this video, we'll talk through the 2021 Higher Chemistry paper. I'll explain how I would approach each question. In question number 1, we're given a reaction and we're asked about how best to separate aluminium carbonate from the mixture. Aluminium carbonate is a solid. You want to remove a solid from solution. Filtration will be the best way to separate a solid from solution. Distillation, we would want to separate mixture of liquids, which is not what we do here, of liquids. You're evaporating, you remove water typically from a solution to make a solid, which is not what we want to do. And if you're collecting over water, that's to do with collecting gas. Again, not what we're asked to do in this case. Next one, we're asked about the difference in size of sodium and chlorine atoms. If you look in the data booklet, we want to check, are they in the same group or are they in the same period? You can see that we have sodium and chlorine in the same period. Any question asking about differences in their properties of elements going across a period, we are going to be thinking about the number of protons in the nucleus. That's what we've got. If the question was talking about groups, we want to talk about the number of electron shells or energy levels that atom would have. And not for this question, but that is what we would end up doing. Next question, we are turning carbon dioxide solid into carbon dioxide gas. Our internal bonds, the carbon to oxygen bonds, will still be present after you've turned it into gas. We're not breaking any of the intramolecular forces. That means that I can rule out A and C. Because we have a symmetrical molecule, this means that that molecule is going to be non-polar, and the strongest force of attraction in non-polar molecules, or between the molecules, will be London dispersion forces. In this next question, we need to think about what electronegativity is about and what it means. It's the attraction for bonding electrons. If you have something with a high attraction for the bonding electrons, they will tend to gain electrons. This will mean that that chemical will itself be reduced. It will help other elements to be oxidized. It will help the other things to lose electrons. A is going to be our correct answer. In question 5, we're asked about the viscosity of two different chemicals. That is a measurement of the thickness of the liquid. What we are shown is that the ball bearing passes more quickly through the chemical X. If it moves more quickly, that's got to be the least viscous chemical. And viscosity is linked to the strength of intermolecular forces. If it's least viscous, it's got to have the weakest intermolecular forces. See what the question actually wants is. So chemical X is the least viscous of the two. Means these two ones cannot be correct. And now we switch over to talking about Y. And therefore Y is more viscous because it's got these stronger intermolecular forces, which means C is our correct answer. So watch out for questions where halfway through the table they switch their focus. So left hand column is to do with chemical X, and then the right hand column is to do with chemical Y. Next up, we're asked about the enthalpy change for a particular reaction. Here we're looking at the ionization energies, and we need to decide which ionization energies we are dealing with. We would first go from Be with no charge to Be 1 plus, an electron being lost, and that is the first ionization energy. We would then go from Be 1 plus to Be 2 plus plus electron. This means that we're going to need to take our first ionization energy and add it to our second. So we went first plus second. We then go to the data booklet We'll shuffle down to the ionization energies. We have beryllium. The two values that we're needing to use are 900 and 1757. We look at our answers. I'm going to go straight for C first of all. The has to be bigger than 1757 alone because we're adding 900. You can either just do it in your head, as I could possibly do, or we can take our calculator, add them together, and we get 2657 as our answer. Next question, we're asked about an isomer of pentanoic acid. First thing I would do in any of these questions is think about the number of carbons that we have. Pent means we've got 5 carbons. Methyl means 1 carbon. Prop means 3 carbons. Means we would have a total of 4 carbons. I can rule that one out just because it doesn't have enough carbons. We need the same carbons, hydrogens, and in this case, oxygens. That's ruled out. Next one, we've got prop meaning 3, meth meaning 1. Again, giving you 4. Ruling out B. Ethyl means there would be 2 carbons. Butanoate would give you 4 carbons. That equals 6. Again, not going to work. Last one, we have 2. And we've got 3 from the propanoate. Gives you 5 in total. It has to tick the box of having enough carbons. If that was correct for more than one of them, what you could then do is think about the functional group. Here we've got an oic acid, meaning it has to have double bond O to an O and then a H. And we'd have all our H's around in the chemical. This means that our answer has to have 2 oxygens in it. Now this could either be an ester or a carboxylic acid. And that's another way you can narrow down which options it could be. Could draw them all out, but to save time, if you look at the carbons first, then think about the functional groups, then you can move on to any hydrogens that they've got. If need be. Number 8, we're told about 2 different painkillers and we're asked which statement is true. Let's go through them one by one. Both of them are ketones. To be a ketone, we need to have C double bond O, where that carbon is attached to 2 other carbons. What you need to watch out for is you cannot get zoomed in too much. You have to look, slightly expand your view. So we have a C double bond O, however, that is part of a C double bond O to an O. That is an ester link. Similarly, at the top, we have a C double bond O. In this case, this would give you a carboxylic acid or a carboxyl group. We then have, again, a C double bond O, but this time it's part of an amide or peptide link. So just because it's got a C double bond O doesn't mean it necessarily has to be a ketone or indeed an aldehyde. That means that A is incorrect. Next one, aspirin, which is the left-hand chemical, contains a carboxyl group and an ester link. Well, I just showed that as I was looking at the double bond O's. Paracetamol contains a hydroxyl group. Oh yes, we do have a hydroxyl group, but we do not have a carboxyl group. Carboxyl groups are C double bond O, O, H. Neither contain an amide link. Well, that's incorrect because paracetamol does contain a peptide link. So B is our correct answer. On to number 9. Which isomers would produce acid when warmed with potassium dichromate? This is the oxidation of alcohols we're discussing here. You need to be aware that primary alcohols will react with oxidizing agents such as potassium dichromate to first form an aldehyde, then onto a carboxylic acid. This question is just asking us which 2 of these are primary alcohols. To figure that out, we look at the carbon attached to the hydroxy group. So this one has the OH on it. It is joined to 1 other carbon, meaning this will be a primary alcohol. On to the next one, we're focusing on this carbon because it's got the attachment to the OH group. This is secondary because there are 2 carbons attached to that carbon. On to the next one. Here we've got 3 carbons attached to that one, making that a tertiary alcohol. Last one, focusing on this carbon connected to the H group, which again will give us a primary alcohol. Therefore, 1 and 4 would turn into carboxylic acids when you react them with oxidizing agents. On to number 10. An aldehyde is converted into an alcohol, a reduction reaction takes place. So we have to try and draw or figure out what would be produced when we reduce this aldehyde. I know it's an aldehyde because it says al at the end. This means that we've got to have the double bond O with a H on the end. It's butane now, so I need to put 4 carbons like so. Got a methyl group off of the second. That'll be a CH3 here. Then my in like so. We are going to convert that into an alcohol. If I copy this over to here, what I need to do then is I need to get rid of the double bond to oxygen. That's then going to allow me to put another hydrogen on to make the hydroxyl group, and we need a second hydrogen joined on at the bottom. This is adding on just 2 hydrogens, which means we're going to have 2 more than 86, which means our answer is going to be 88. You could count them all up, so another way you could do it is count up all your carbons. So we've got C5, we've got H5, 6, 7, 8, 9, 10, 11, 12. Then we would have on the end, and you could then count that up and work out what your answer would be. Here we're asked which following compounds would react with sodium hydroxide to form the salt sodium propanoate. We have got a neutralization reaction. We have an alkali and we are forming a salt. Lies on as known that acid plus alkali base gives you salt plus water. Since we're using sodium hydroxide, the beginning of our salt is going to be sodium, and the second half of the name has to come from the acid, and we are told that it is propanoate. This means that our acid would have to be propanoic acid. That's how we end up at sodium propanoate. This means that we're going to have 3 carbons within it. We're also going to have a C double bond O OH. Have to have our carboxyl group. With these questions, you need to be able to recognise what type of chemical we've got. The way that this first chemical has been laid out, this is most likely to be an ester, where you have your C double bond O, and then you have your oxygen, and then a carbon coming off like that. Similarly, for the next one down, it's going to be in the same boat, because the COO is right in the middle. We're going to rule them out because we're looking for an acid. Let's get rid of them. What you need to watch out for as well in your count, you need to count this carbon as well in your total number of carbons. So C has 3 carbons in total. 3 carbons would be prop. That's going to give us propanoic acid. Something that comes up quite a lot, where the COOH is separated from the rest of the carbons, but you count it in the longest chain and you count it in your name. So C would be correct here. Denaturing is to do with changing shape. And when you change the shape of a protein, you're breaking the hydrogen bonding. So the forces of attraction that were holding it together, it's those hydrogen bonds that would be broken that would change the shape. If you were breaking it up into its amino acids, this would be hydrolysis, where you split the peptide bonds. Similarly, well, C straight up says that. That's hydrolysis. If you're eliminating water molecules, this, in terms of proteins, would likely be referring to a condensation reaction when you're making them, which is not what we're asked about, so our answer would be B. When it comes to fats and oils, what I base this thought process off of is the fact that oils tend to be liquid. If it's going to be a liquid, this means that it's going to have lower melting point. The reason it has a lower melting point is that it's got weaker intermolecular forces. This happens because there is less close packing of the molecules. If they were packed really tightly together, that would give you stronger forces. The weaker the packing, the weaker the forces, or the less closely packed it is, I should say. Less closely packed. Now, the jump we need to do here is we need to link that to how many carbon-to-carbon double bonds. If you have more carbon-to-carbon double bonds, that forms little kinks in the chains, which means they are no longer able to fit as closely together. This is to do with unsaturation, so it's more unsaturated, which means it's going to be less saturated. So we're looking for less saturated and lower melting points. Okay, so I've just clocked that I've read this question wrong. So B would be true for oils. However, the question is asking us to focus on fats. So the statement that we're looking for fats is the opposite. So oils are less saturated, which means fats are more saturated. Oils have lower melting points, therefore fats have higher melting points. So C should be our correct answer. My thought process was totally correct, but I just misread what the question was wanting, so I had to just go focus on the fats that gives us C as our correct answer. Okay, and this next question we're asked about antioxidants. Antioxidants are chemicals which prevent oxidation, which prevent the loss of electrons. It does this by giving its electrons to other chemicals, which means it will be an electron donor. An oxidizing agent causes loss of electrons, causes oxidation to happen. That's exactly the opposite of what we are trying to do with antioxidants. Because we're wanting the one that's not true, B is going to be our answer. Reducing agent is going to cause gain of electrons, which will prevent oxidation. That is true about antioxidants. And the free radical scavengers act with radicals to form stable molecules. And it is something that we're looking to do with free radical, with the antioxidants. Means it is not our correct answer in this question. Next one here, we're asked about our different steps in free radical chain reactions. We have initiation. And then we have propagation. Moving on to termination. Way I look for it, I'm looking for the radicals, which are shown by the dots. In the first one, we have radicals on the left, but no radicals on the right. This means that we have stopped the reaction, gives us our termination. Next one, we had no radicals on the left. We now have got radicals on the right. Therefore, this is going to be our initiation because it's starting off the reaction. Similarly, for C, it's same as A. It's also termination. There's radicals, the ones with the dots on the left, none on the right. This means by a process of elimination, our answer D is going to be propagation. We have a radical on each side. It keeps the reaction going. D is our correct answer for that one. For question 16, it's asking us about rates of reaction. One thing we could do is we could turn our times into rates, and rates are going to equal 1 over time. The other way we could approach it is we can just look and see, well, the first statement A says that if you do a small increase in temperature, you get a large increase in the rate. If you half the time, that means that you've doubled the rate of reaction. This means that A is looking good to be the correct answer. Activation energy increases with increase in temperature is incorrect. If the question was talking about kinetic energy instead of activation energy, that would have been true. Doubling the temperature of the reaction doubles the rate of reaction. That would mean that we are dealing with these two here. So we're going from 20 to 40. Well, if we put those values in, we've got 1 over 60 for temperature 20, and we've got 1 over 14 for the 1/14 for temperature 40 degrees. That is not a doubling of the rate, meaning that C is incorrect. The reaction is slowing down with increase in temperature, while the time it takes for the reaction to happen is getting smaller with temperature, meaning that D is incorrect. On to number 17. This question, we're given a graph. We're asked about the concentration of potassium iodide solution used in a reaction that took 5 seconds to complete. The graph is to do with rate and concentration, so we're going to turn our time into a relative rate. So our rate is going to equal 1 for T, which is going to be 1/5. That's going to give us 0.2. And then find 0.2 on our graph here. Run that across. Run that down. We get that we're 1 box away from 1.0. We need to decide what we're going to go up in each jump. 5 boxes equals 0.2. So 1 box is going to equal 0.2 divided by 5, which is going to be 0.04. This means that we are 1 box away from 1. So to get our answer, we can do is 1.0 take away 0.04 equals 0.96. Shuffle down and we find an answer that matches that, giving us our answer. With this particular question, if you look at the options we're given, we know we're close to 1. E is the only value that's close to 1, so that could give you your answer as well. Something you need to watch out for as well is feeding off at the correct point. There have been times I've seen people who've used 0.02, got muddled up with the numbers, which would run you off a different value, an incorrect value. On to number 18. We're asked about an exothermic reaction taking place at room temperature. Exothermic releases heat, and that means that our value at the end is going to be less than what we started at. Release energy. We're going to start off here. We're going to have our value down at the bottom. A does have a lower value at the end, so it could be A. B is also exothermic because it's lower at the end. C is the wrong way around. This would be an endothermic reaction, and D would be incorrect because that is also endothermic. Going up, we need to think about room temperature. Room temperature, we're going to have low kinetic energy. This means that we need a low activation energy, so our jump up has to be fairly small. A has quite a high activation energy, so the barrier that needs to be overcome be quite difficult to do, especially at low temperature. Ruling out A, leaving us to B as our correct answer. On with number 19. Asked here about the volume of the products being half the volume of the reactants. In this question, we need to be thinking about gases. I'm going to chop away anything that's not a gas, allow us to get our answer. We look at our number of moles of gas on each side. In A, we have 3 on the left, we have 2 on the right. The products are not half of the reactant, so that one's ruled out. Next one, we have 1 and 1, so it's equal, not our answer. We then have 4, 2, so our products are half of the reactants. And then the last one, you have 1 to 2, the other way around, where the products would be greater than the reactants. We can rule that one out, making C our correct answer. In this next one, we are asked about using percentage yield in a slightly different way from usually. In the data booklet, we are told percentage yield equals the actual yield divided by the theoretical yield. We are already told our percentage yield is 80, and the 80 equals, well, it says which of the following mixtures would produce the 0.8 moles of ester. That means that the 0.8 will be our actual yield. we are trying to work out the theoretical yield. Get that there. If we rearrange this equation, we're going to end up with x equals 0.8 over 80 times 100. We can bump that into the calculator. 0.8 over 80 times 100 give you 1 mole. This means that we need to have a theoretical yield of 1 mole. We have 1-to-1 ratios at the top. That means that we would want to use 1 mole of each reactant, which would then allow us to make 1 mole of our product. Finishes off the question. Another way of thinking about it is, well, if you've got a yield of 80%, you're not fully efficient in turning the reactants into the product. You're only working at 80% efficiency. You need to use more of this reactants to form however much product you want. So if you're wanting 0.8 moles of the ester, we need to use more than 0.8 of the reactants, and D is the only one that fits in that category, giving us that as our correct answer. On to number 21, we are asked to figure out some information about this graph. Things that we can figure out is that it's favoured by lower temperatures. If it's favoured by lower temperatures, that means that the reaction is going to be exothermic. In these equilibrium questions, if you affect a change, the system will try and oppose that. So if you lower the temperature, the reaction will increase the temperature by favouring the exothermic reaction. This means that A is going to be correct. Let's look at the other ones. All reactants are converted to products at 250 and 300. This would mean that you'd have 100% yield. There's no set of conditions in this graph that give us 100% yield. That would have to go roughly along there. We have no conditions that give you 100%, meaning that B is incorrect. If you increase the temperature, increases the yield. Again, not true, because the higher values of yield are obtained using the lower volume. Rid of that. Increasing the pressure after 200 atmospheres has no effect. That was true. We'd be looking at roughly sort of here. After this point, there would be no difference in values, but in both graph lines, they are increasing as you go past that point, making that answer also incorrect. A stays as the correct answer. Next one, we've got a little calculation to do with number of moles and concentration. Our data booklet tells us that N equals C times V. Times V. I am going to start with the sulfuric acid because I'm told 2 pieces of information about it. I know that I've got a concentration of 0.2 moles per litre. We need to divide our volume by 1,000, give us 0.05. 0.2 times 0.05 gives us that gives us 0.01 moles of sulfuric acid that's been used. We're dealing with these 2 chemicals here, which means we have got 1-to-2 ratio, starting with the chemical we started with. That's the 1 KOH or 2, which means if we've got 0.01, we would need 0.02 moles KOH, which is what the question wants us to tell them. So the answer is just B. On to number 23. Here we're given information about a chromatogram that's been ran. We are told information that larger molecules travel a shorter distance and less polar molecules travel a greater distance from the baseline. First statement says that P is less polar than S. If P was less polar than S, then P would travel a greater distance than S. So we've got P and we've got S. That is not true. Let's rule that one away. Next one says that Q is larger. Larger molecules travel a shorter distance. We're up on this one here. That was Q and E. Q travelled further, so Q would then be a larger molecule. That one away. R is more polar, with less polar molecules travel a greater distance, and more polar would travel a shorter distance. So R would travel a shorter distance than P. Well, that is correct. Let's tick that or circle that as our answer. If S was a smaller molecule, S would travel further. Q travelled further, so Q would be smaller than S. So that one's incorrect. C is our correct answer. On to number 24. If we're going to go on to use our results from a titration in a calculation, we want to use the concordant results. Those are results within 0.2 centimeters cubed. When we look at our values, the two, this one and this one are too far out. These two are within 0.02 of each other, meaning that's the values that we'd use. Your average is going to sit in between two values. That's going to give us an answer of A 20.35. Your other option is to add them together in your calculator and then divide it by 2 to get your average of 20.5. Last multiple choice question. We've got another equilibrium question. We're told information about changing the pressure and changing the temperature and what happens to colour. First thing says that increasing the pressure causes the mixture to go paler. You increase the pressure, it favours lower number of moles and number of moles of gas. Both of these are gas, so we don't need to think about that. Lower number moles. In this case, we've got 2 on the left and 1 on the right. If you increase the pressure, that means that the right hand side would be favoured, and it tells us that this is our paler side because the reaction has gone paler, which must mean, based on the rest of the information, that the NO2, which is on the left, has to be the brown colour because it goes paler when you move to the right. So we're either on A or C. If you increase the temperature, we are going to favour the endothermic reaction. And it's became darker, which means it has to have favoured the left-hand side. What this is telling me is that going back the way is endothermic. Because when you do increase temperature, it's moved to the left, which makes it more brown. We are asked, crucially, about the forward reaction. Backwards one is endothermic. The forward reaction has to be exothermic. And that would be favoured by decreasing the temperature. So A is our correct answer in this question. In question 1, we're asked about electronegativity, and we're shown a graph of the trends in electronegativity for the first 20 elements. Asked about the trend as you go across period 2 from lithium to fluorine. If you don't know which atomic number lithium and fluorine are, we can use the data booklet. We can see that we are dealing with starting at atomic number of 3 going along the period. Therefore, if we go in here, we're dealing with this part here. You will find that as we go across the period, those values are getting bigger. We just want to say that the trend is increasing. Just want to state, we don't need to explain it in this question, just to say what happens. There are no electronegativity values shown for elements with atomic numbers 2, 10 and 18. Let's look. See what they are. They are indeed noble gases. We're asked, why do we have no electronegativity values for the noble gases? As it tells us at the beginning of the question, it's a measure of the attraction that an atom has for electrons of a bond. For that, the noble gases do not form bonds, therefore they cannot have an attraction for electrons in a bond. And that's just what we'd say. So they not form. Specifically, we're talking about covalent bonds, why they don't have a value for them. In this question, we're asked to explain why the electronegativity of elements decreases as you go down a group. As I said previously in one of the other questions, we're talking about ones in the same period. We're talking about protons. If you're going down the group, we should be talking about electron shells. We have got our number, electron shells increases as less fraction place for bonding electron. Given a graph that allows us to predict the bonding in particular chemicals by using average electronegativity and difference in electronegativity. Using the information, state the highest average electronegativity in ionic. So we're dealing with this one, lock in there. You want the highest average. Average goes across the way, which means we're wanting the value to the furthest right of it, which would be over here. Run that line down. Get us to 3 boxes past 2.5. Each box would be 0.1. 0, 0.1, 0.2, 0.3, 0.4, 5. That works. So we pick an answer of 2.8. That's just the value we want for that one. So watch out when it says highest. You need to look at the scale, and our scale runs from left to right, so it's the furthest right. Next one, we're given information about magnesium and nitrogen, and we're asked to put a cross on the correct position on the graph above. First, need to work out the average. Get the average of the two, add them up and divide by 2. 1.2, add 3.0 over 2, 4.2 over 2 gives us 2.1. Then our difference, just take them away from one another. We have 3.0 take away 1.2, which gives you 1.8. 2.1 and 1.8. So average goes across the way. So I'm wanting 2.1 here. So, and then we had 1.8. Same scaling. Good. You'd want to have our value crossing over that point there. And that gets us our answer in there. Next one. We are now discussing ionic chemicals and an ionic formula for lithium sulfide. First thing I would do is just find out the normal formula for lithium sulfide. Use the data booklet. Find out group they are in. Lithium is in group 1. Lithium will therefore lose 1 electron, and it will have a valency of 1. Sulfur, which is over here, have a valency of 2. A 1 and a 2, swap them over, giving you 2 and 1. And our normal formula would be Li to S. Couple ways to do the next bit. The thing I like to say is, well, if it's a metal, lithium is going to lose an electron. It's going to have the positive charge. It'll have a charge of 1 plus. And the sulfur needs to gain 2 electrons, means it's going to be 2 negative. When I'm then going to rewrite our formula as an ionic formula, I am just putting in the charges as I go. So lithium has got a 1 plus charge, and there are 2 of them. Our sulfur is 2 minus, and we only need 1 of them. You get 2 singly positively charged lithiums, that's 2 plus overall, and then our 1 sulfur have a 2 minus, so our charges balance out, making this our correct answer. In this next one, we're looking for two non-metal elements with an electronegativity difference of 1.5. We'll have to suggest names for those. So if we down here, we're looking for a difference of 1.5. Roll it a little bit. Try and pick out some of them. It needs to be non-metals. That's another thing we need to consider. So I've spotted that bromine and titanium have a difference of 1.5, but titanium is a metal, so that cannot be correct. I'm going to go away from that. I've been staring at this question for quite a few minutes. I've clocked the fact that it was using the values from the old data booklet, so I went and found that and brought it up here, and we'll start again and hopefully get an answer that pops out quite nicely. If we look first of all at, say, something like fluorine, and there's one there. Carbon would have a difference of 1.5, so carbon, fluoride, carbon and fluorine would work quite nicely. Potentially some other ones. Sulfur, there's sulfur. If you use fluorine again with sulfur, you get a difference of 1.5. Are there any more? We could have boron and oxygen, there we go, would have a difference of 1.5 as well. This question needed to be answered using the older data book values to get a difference of 1.5. If it was using the new values, it would maybe say a difference of 1.6 rather than 1.5. So using old data booklet, we had carbon and fluorine, or sulfur, fluorine, or boron. The one I have there. This question states that we have one element that has a greater attraction for bonding electrons than the other. The type of covalent bond, it's either going to be polar or non-polar. Polar covalent bonds are found when there is a difference in electronegativity. Same, it would be non-polar covalent as your answer. Next one, we're discussing carbon. We're told about carbon fullerenes and carbon diamond. We're asked to give them another form of carbon. Carbon graphite would be in here as our answer. Next one, we are changing from solids into gases directly in a thing called sublimation. We're asked about the strongest attractions broken in carbon diamond and carbon fullerene. We need to be aware that carbon diamond is a network, whereas we have covalent molecular or fullerene. The reason this is important is if you have a covalent network that you're breaking, strongest attraction will be covalent bonds that are broken. If you have a molecule like fullerene, the strongest attractions broken will be London dispersion forces. This is also shown by the fact the values, the temperatures that the chemicals will sublime at is vastly different for that. So because diamond, you're breaking strong covalent bonds, you have 3,825, and it's the weaker London dispersion forces that result in a 550 for the fullerene. On to the next one. We are told that fullerene can react with bromine solution, just a bromofullerene, and we're asked to determine the number of double bonds present in a molecule of that chemical. We're going to have addition reactions happening. If you have one carbon to carbon double bond, something like that. When I react that with bromine, I will break the double bond, add on bromines. That's that. Every one carbon to carbon double bond would be broken and two BRs, two bromines would be added. Therefore, if we're adding 24 BRs, that's got to be 12 carbon to carbon double bonds. is every double bond requires 2 bromines to break. Answer, which in this case would be 12. Next question wants the atom economy for iron. First, we'd get the relationship from the data booklet here. The key to this question is you have to take into account any balancing numbers that are involved, otherwise you'll end up with the wrong answer. It's iron, which is the Fe. This means that we're going to have to do 2 times 55.8 on top. The reactants are on the left. We have 1 Fe2O3, which is 159.6, plus 3 times 28 for the CO. That all has to be times by 100. 111.6 divided by, I'll do the 3 times 28 first, plus 159.6, 243.6 times 100. Scientific calculator, you could 243.6 times 100. 45 point. Now I'm going to go for 3 significant figures here, which would give me 45.8 as my answer. 8, that is in percent. On to the next one. This one, we're asked to work out the enthalpy change for our reaction at the top. This is using Hess's law. We have got our target enthalpy change at the top, and I need to figure out how the rest of them all fit together. The way I would do that is go and look for the first chemical, which is CH4. I'm looking to see which equation that is present in, and that is present in the third equation here. So next question is it on the correct side? Well, it's on the left hand side of both of them, so that's good. We don't have to flip it round. There is 1 in each of them, which means I just want to use the value of delta H3 as it's written. Don't have to change anything. Works out. Next chemical would be H2O gas. I have spotted that this is in 2 equations. What this means is I'm going to leave that alone just now, because it should or might fix itself just by joining up the other ones. You skip over to CO gas. That's in equation 1. It's on the wrong side. We have it on the right in the target and left in delta H in equation 1. What I want to do is do a negative sign. I need minus delta H1. Still one of them, which is what we wanted, so that's fine. Moving on to the hydrogen, we've got 3 hydrogen gases on the right of that one. We want it on here. It's on the wrong side. I need to put a minus. There's only one of them in the second equation. I'm going to have to use 3 delta H. At this point, I could just go ahead and just plonk in all the numbers. What we can do is a way of checking if we've got the connections between them correct. What I would do then, I'm wanting to check it, is I'm going to rewrite these equations, having flipped it round for delta H1, and having switched it round and times it by 3 for delta H2. Now I've rewritten them, taking into account any ones that need flipped or times by, in this case, 3. What I'm looking for now is if I got my left hand side and my right hand side, I'm looking for anything that appears on both sides that I can then cancel away. And by doing this, this should leave me with just the target equation that was at the top. I'm clocking it. I've got a CO2 gas on each side, so let's rule them out. Also got half an oxygen, 1.5 oxygens is 2 oxygens in total, which gets rid of these 2 ones there. We have got 3 H2Os on that side. We'll get 2 H2Os on that side. So what will happen is this will knock this down to just 1 water on the left hand side. Nothing to cancel away the CH3s. I've got nothing to cancel away the waters now. That should leave us with that. So if I extract out that are left over, that would give me CH4 gas plus H2O gas goes to CO gas plus H2 gas. Now, if I take that with me, we can then go and see, does that match what we've got at the top? Well, yes, it does. So CH4, H2O, CO, and 3H2s matched up. What this means now that I've proved that, this means I can just go ahead and plop the numbers in and type it in my calculator and get my answer out. This allows us to know if we have got the correct relationship between them. If something stayed there, so for example, if I still had oxygens present in my final equation, I've done something wrong because there's no oxygens in target. So there has to be some sort of combination of these that gets rid of the oxygens, which was what we have found out here. Putting in the numbers in a couple of different ways. I just copy the numbers in. Calculator can deal with the negatives for us. I know some people like to change the numbers over beforehand. That's totally fine. So I've got I've got minus 891 minus 283 and minus 3 times 2, 6. If you wanted to deal with the signs, we could say then that, well, minus 891 stays the same. And they're going to be plus 283. Minus is going to be plus 3 times 286. Just use lots of brackets in your calculator. You could do that as well. I'm going to do 3 times 286 first on that calculator. Plus the 283 minus 891. And that gives us a value of 250. It's going to be 250 in kilojoules per. Can skip past the stage where you prove if you've got the correct relationship. Problem with doing that is you will not know if you've got the right relationship, whereas by proving it, I can trust that I've got them in the right places. I can get my answer out at the end. In this question, we're asked to discuss collisions and their importance to chemical reactions. First thing I would do is talk about collision theory first of all. Colliding molecules must have enough kinetic energy to break their bonds and form new bonds. This is what's known as the activation energy. Activation energy is the minimum energy required for the reaction to take place. Collision also has to happen at the right orientation to allow the bonds to be broken. Sometimes described as being the collision geometry. Next, we'll talk about the factors that affect the rate of reaction. If you increase the temperature, you provide more kinetic energy. This will mean that more molecules will have kinetic energy greater than the activation energy. Increase the concentration, you're going to have more particles colliding, higher chance of successful collisions. If you decrease the particle size or increase the surface area, this will allow for more collisions to take place, and this will increase the reaction rate. Next one we could talk about is the effect of a catalyst. Adding a catalyst lowers the activation energy. So more particles will have kinetic energy greater than activation energy and can react. In order to pick up all 3 marks, we have to give a good answer, 2 marks, a reasonable answer, and 1 mark for a limited answer. There are some other parts of chemistry we could talk about. For example, equilibrium, having that balance between products and reactants. Talk about endothermic reactions. They're favoured by different temperatures. The conditions, again, favour one way or the other. And there's probably some other ones that I'm missing. But as I said, we only want a good answer to pick up our 3 marks. Moving on to question number 4. We're asked to use bond enthalpy values to explain why nitrogen is so unreactive. Go into our data booklet, go down to page 11. There's a value of 945 kilojoules per mole. Nitrogen, very high on density. Requires a lot of energy to break. In this question, we have to draw a correct diagram for a particular reaction. First of all, we've got air being bubbled through potassium hydroxide solution to remove carbon dioxide. That one first. We want to have some sort of container. Test tube is probably our easiest thing to draw. Here, this will allow the gas to pass in and go into our potassium oxide. Next, we want to have a second tube coming out. Take with it any of the chemicals. Here. So, want to close off stopper, trying to make sure that we don't put lines through our pipes. Using a ruler would make it look ever so slightly neater than this, but we have ability for the gases to pass through into a solution of potassium hydroxide. Anything that's not taken in by the potassium hydroxide can come out through the second pipe and on two. In stage 2, we're passing them over heated copper. Remove the oxygen before the remaining nitrogen is collected. This one we're asked to pass it over the copper. Means I want to put the copper in the middle. The gases that go from left to right hand side, it has to pass through this. This we need labelled. Do this in two ways. We can either say this is copper. Another option would be to put arrow saying that we are heating this. Could try draw Bunsen burners. I would definitely not recommend that. Just an arrow saying that you're heating it. Or if you label the copper as heated copper, that's telling the marker that you it to be formed, and this will allow you to pass the gas out at the end. Next question, we're asked to calculate which reactants was in excess. Turn both of them into number of moles. That will make the comparison a lot easier. I'm going to start off with the nitrogen. We are told the volume is 0.9. Work out the number of moles. At this point, we're either going to be dealing with N equals C times V, or we're going to be dealing in molar volumes. For this question, we're talking about a gas. Also, no information about the concentration means that we need to be dealing with molar volume. A couple of options for doing this. One way that people like to use is equation. Now, this equation it's derived from one in the data booklet for masses in GFM. The mass is the portion of the mass that we've got. In much the same way, when we're doing it with molar volume question, the volume that we've actually got is our V, and it's on top. Gram for mass is the mass of 1 mole. The molar volume is the volume of 1 mole. One thing we can do is we can use for MV, for N equals, need our volume in litres, which we have, 0.9 on top, divided by down here. Telling us down here is telling us that molar volume is 24 litres. The volume 1 mole is 0.9 over 24. Use our calculator. Gives an answer of 0.075. Moving on to our next chemical, which is lithium. We're given the mass, so we're going to use N equals M over GFM. Mass is 0.5. GFM we can get from the data booklet. That value before, don't remember it. Here. But value we're going to use is 6.9. Pop that in here. 9. We're doing N equals M over GFM, so the mass divided by gram formula mass. Back calculator, what's divided by 9 gives us 0.072. And one of the main mistakes people make at this point is they will look and just straight compare the two values we've got. You have to consider the molar ratio to figure out which one's in excess. If it was a 1-to-1 ratio, it is not in this question. Other questions, you can just compare them straight away. So what we're going to have to do is look at our ratio. Now, in this case, I'm going to do the ratio the same way as I calculated them. I have nitrogen to lithium. In front of the nitrogen, there is no number. This means this must be a 1. Put into my ratio. For the lithium, there's a 6, which means this means that the moles of lithium needed is 6 times as much as the moles of the nitrogen. What I would then do is I'm going to explore the two possibilities. Either I'm going to use up all my nitrogen, in which case I'm going to use all what I have got from down here, 0.0375 moles. What I would need to do to that is times that by 6 to get how much lithium would be needed to make that react. I take 0.0375 times 6. This would mean we need 0.225 moles of lithium. If we compare how much lithium we would need with how much lithium we've got, we are unable to make that happen. This means we will not use all of the nitrogen. We do not have enough lithium make that work. Could then go and get our answer from there. What I would tend to do is I would go and explore the other possibility, which is use all our lithium. Ever slightly. Want to use lithium. This time I'm putting in the number, the value we have of lithium, 0.0725. This time to work out how much nitrogen we would need, we need to divide by 6. Back to our calculator. 0.0725 divided by 6 gives us 0.012 moles. If we now look at how much nitrogen we've calculated we would need versus how much we have got from the question, we do have enough of the nitrogen to make this happen. This means we will use all the lithium. All lithium used tells us this is our limiting factor. If we add more of it, we can make more of our products. Is some nitrogen left over? And that leftover means it's our excess one. So our nitrogen is in excess. Work out number of moles, compare them using the ratio, then working out whichever one is used up completely is going to be your limit factor, and then the one that you have some chemical left over is going to be excess. Moving on to our next question. Talking here about reducing copper 1 ions to copper atoms. Copper 1. First thing I would do is start off with what we're told. So we're told we're starting with copper 1. This means it's going to have a 1 positive charge. Metal, it's going to lose electrons. So it's going to start off 2 positive. On the other side, it's going to copper atoms. This means it will have no charge anymore. Let's see. I would then go to the data booklet, down to the page with the reduction reactions on them. Now, might get lucky and might have copper 1 in here, but if not, we can just tweak one that they do tell us. Copper, we've got copper there, that's copper 2 plus. Got copper 1 plus going to copper 2 plus. Not entirely helpful, so let's look at underneath it. Focus on things that I'm picking up from here is that wherever the charged ion is, the electrons are beside it. On the other side, it's just the atom with no charge as a solid there. You go from 2 plus to no plus, so to get rid of the 2 positive charge, we've added 2 electrons. We only have to add 1 electron to get rid of the 1 positive charge. I'm going to just add in the AQ because it's in solution plus electron and make for copper solid. We're asked to give them a reduction. Another thing that can help is all these equations here are reduction. They all have the electrons on the left hand side. They are gaining electrons. Both of them taken into account. We've got our correct answer here. Next one. We're asked to describe the structure of a solid ionic compound. The word that we're using, word that gets paired with it would be a lattice. We have ionic lattice as our structure for lithium nitride. Other potential options, if it was a different chemical, you could have a metallic lattice, the lattice being the structure part, metallic the bonding. We have covalent bonding, that is a network structure. Got covalent bonding, and we have molecular structure. For structures as well, kind of more of a lack of structure, but the onatomic, just one atom existing. Because it's ionic, paired with lattice. Next one, got to give the term, sorry, we've got to explain what the radical is. It's a substance with an unpaired electron. So molecule, atom, there's different versions of it. So substance, species, paired electron. Not a 3 electron, not a single electron, it's an unpaired electron term that you want to use. This question, we're asked to use bond enthalpies to work out the value for the radical that is shown, so the nitrogen oxygen double bond in this chemical. Something we need to be wary of. This is not your typical question. Typical question, you work out the total energy for breaking the bonds and making the bonds, and then work out your enthalpy change. However, we are already told our enthalpy change. How I would set it up is I'm going to put breaking first, and I'm looking at the left hand side of the arrow. I need to break nitrogen, triple bond nitrogen. I've got 1 of them. Also going to have to break oxygen double bond, again with 1 of them. Going over to my making part, I've got N double bond oxygen, and I've got 2 of them. We'll be able to find the first 2 in the data booklet in triple hunt for it. Oh, we used it earlier. So it's 945. Pop that in. Oxygen, double bond, just above it. 8. What I would then do is I would total that up, so I get my total energy for breaking the bonds. 1443. When it comes to the making bonds, well, I know that I've got 2 times whatever that value is, which is what we're actually going to be working out. And on the far side, well, the difference, so the enthalpy change is the difference between those 2 values. We are told that goes to 1. The way that I would kind of tend to do these ones is, well, breaking a bond requires energy. This means that that's going to be a positive enthalpy change when you put energy in to break something. Making bonds releases energy, exothermic, so it'd be negative. But how we would do it is we would typically take our breaking number, so the one on the left, that's going to be take away making, That gives you your enthalpy change. The way it's working round, we need to rearrange this to get what our values would actually be. Well, I know that 1443 minus. Make this life easier, I'm just going to call this x. It doesn't matter what term you use, but I've got two of them. Maybe have that take away goes a 1. So as we rearrange this, we'll get that 1443 minus 91 to x. So when I take those two numbers away from one another, 1352 to equal x. So if we just want to know what the value is for just one of them, so the bond enthalpy half of 1352, then divide this by 2 to give us 676. Going to be a positive number. Moving on, talking about the different steps in free radical chain reaction. We have options, we have initiation, we have propagation, and termination. Here we've got 2 free radicals coming together. That's going to stop the reaction. That's going to terminate our chemical reaction. Initiation, we would make radicals. The propagation, we would have radicals at the start and at the end. It would keep the reaction going. But in termination, we're using up the radicals, so it's going to be termination. This next one, we're asked to draw a possible structure. First thing we need to know is how many bonds each of them makes. That's the most important thing. Your marker's going to check, does your, for instance, hydrogen make 1 bond like it's supposed to? Your nitrogen, 3 and 2. How I know that is, here we've got our oxygen, gain 2 electrons to have a filled outer shell, have a valency of 2. Then got our nitrogen, which is one more step away, so it's going to be 3, valency of 3. Our hydrogen is in group 1, and things in group 1. That. So as long as we do the correct number of bonds, we should be fine. I'm going to start off with my nitrogen in the middle. That can make the most number of bonds. I then put an oxygen here. Double bond that. Now my nitrogen's making 2 bonds, oxygen's making 2 bonds, so the oxygen's fine. Put another oxygen here. Nitrogen's now making 3 H. On there. Another option. We could maybe do it in a ring. Nitrogen, oxygen, nitrogen. Oxygen's making 2 bonds, both of them. This one's making 2, so in here. As long as the nitrogen has 3 bonds, oxygen 2 bonds, hydrogen 1, you fine. Next one, we're asked about equilibrium, balanced reaction, and we're asked about the effect of decreasing the reaction temperature. Negative enthalpy change means this is exothermic. An exothermic reaction will warm surroundings. How I think about this is when would you need to warm the surroundings? Warm the surroundings when it gets colder. So decreasing the temperature favours exothermic reaction. Yeah, so favours if we look at what I've said previously, that means that's our forward reaction. Favours exothermic forward reaction. So moving from left to right. The chemical we are asked about, ammonia, is on that side. Therefore, it will increase the yield of ammonia. You need to identify which direction is exothermic or endothermic. And so your question based on that. Next one, acid balance an equation. How I balance these, I just go through each chemical one bit at a time. We have got 3 carbons on the left and only 1 carbon on the right. That means I need to put a 3 in here. I would then move to one of the other chemicals. So I'm wanting to leave hydrogens and oxygens, so they appear quite a few times. I'm trying to leave them as long as possible. Let's try the nitrogens. Got 2 nitrogens here, 3 nitrogen there. If I times this one by 2, now got 6 nitrogens. Times this by 3, then got 6 nitrogens. Means though, you think my carbons here, because now I've got 6 carbons, 2 times 3. This would then have to be 6 in there. Next, we could look at the hydrogens. Hydrogens, we've got, well, there's 5. We've got 2 of them. 2 times 5, which is 10. This 5. And we need to carefully count our oxygen. 9 oxygens here, times by 2. That gives you 18 oxygens. But 6 times 2 gives you 12. Then got 5 times 1, H2Os, 5, put over here, give you 17, 19. Now, we need to think of how we can fix this. Now, nicely, got 18 versus we could just do half of an oxygen there, knock this down 1, get 12, add the 5, 17, and 18. That works out. That. One of the things that sometimes people are quite against putting half of a particular element, a way around that, and maybe not so much for this one because there's lots of big numbers in there. Option, and it's accepted, is if you use multiples of your values. So instead of having 2, we could put 4 H5N9. Then instead of having 6, we could double that up to give us 12 CO2 plus, instead of 5, we'll have 10 H2O plus 6 N2. Then this time, instead of having half of an O2, you would double that up to give us 1. That would give us answer there. Personally speaking, I would usually prefer to do the bottom part and have them so they're whole numbers in front of them. Because the numbers are quite big and we've already had to like puzzle our way through. In this case, I might actually have stuck with the red balancing numbers that I had previously. Because it's a multiple of the correct answer, it'll work out for that, but you can make your decision as you go. Next, we're asked about why a small shock or bump can cause the chemical to react. It's going to be something to do with activation energy. Activation energy is the barrier that needs to be overcome. So the shock it provides enough energy to overcome the activation energy. Next one, talking about determining the energy released by food, bomb calorimeter. Features of this that help us to get accurate values would be provides a lot of oxygen. So it's got its own oxygen supply for it. So next one could be we've got well insulated. So insulation that prevents heat loss to the surroundings. You're asked about a pupil doing this reaction. That's one of the reasons why the numbers might be lower. Some of the heat would have escaped. Vents lost in surroundings. What the stirrer? The stirrer means it's an even temperature you're going to measure. You're going to have a hot patch of water that you accidentally measure and think that you've got a higher value than you did. temperature. We're given some information. We're asked to calculate enthalpy of combustion. Enthalpy of combustion is the energy released when 1 mole of a substance burns. 2 parts I need to do here. So one, I'm going to work out how many moles this is. N equals M over Fm. So we've got an answer 0.00. We'll go 11. Next, we'll start on the EH equals Cm delta T part question. I'm going to work out what the energy released will be. We are dealing with water being heated, which means the specific heat capacity, or C, will be 4.18. Here, we need to convert that into litres, then into kilograms. So we need to divide by 1,000. That will give you 0.775. That's litres. And then, because 1 centimetre cubed, we are equating to 1 gram, it's going to be 0.775 kilograms. Divided by 1,000 is ready to use. 0.775 times temperature changed. It's going to be 11.9. That is in the question. H equals that, 8.55. That is the energy that was released when the 1 gram was burned, and I previously converted 1 gram into 0.0011 moles. Again, multiple options. The way I prefer doing this one would be to say, well, if I've got 0.0011 moles, that gave out 38.55 joules. We want to know what 1 mole would be, because enthalpy of combustion question. You start at any number and you want to get to 1. If you divide it by itself, it will turn into 1. 0.0011. I want to do the same on the other side. So I need to do 38.5 divided by 0.01. That should give us our answer. Give us 35,045. It's going to be a negative answer because it's exothermic, it's giving out heat. It'll be minus 35,045. You'll be allowed a little bit of varying depending on how you have rounded throughout the question. You want to try and round as little as possible. If you use your completely unrounded answers, what you'd end up with is an answer of 34,078. Your marker will check that you've rounded correctly in order to get to a correct answer. So you want to limit the rounding as far as possible. And at this point, this is what we'd get out if we just used all the numbers unrounded. This question, we're given a relationship that we have probably not came across before. We just need to work out what values go where. We have 57 moles at the top, and we have 80 on the bottom of the auction. This question, I'll need to take it to 3 significant figures. 0.713. Answer. Moving on again. This one is a prediction of the viscosity of a particular chemical. Now look at what the table shows us first of all. So every 6 extra carbons going up by 2.9 in this case. Another jump of 6 carbons, and again that is 2.9 difference. 6 carbons. Both of these two. Here we do have 2.9. Okay, so for every 6 carbons, so plus 6 carbons plus 2.9. Okay. We are going up to 57. This means that, well, if we're at 39, 1 jump would be 45, 2 jumps would be 51, 3 jumps would be 57. So we are going up by 6 3 times. Means that our answer is going to be 3 2.9's greater, you can either just do it step by step, putting in the numbers. What I'm going to do, when I say what's going to be 14.6, because that's the last value we're given, plus 3 times 2.9. That's going to be then 14.6 plus, that will be 8.7. That will give you 2223.3. That's what it tells us. Answer there. And that gets us answer there. If it's the same jump each time, you need to use that value. So it went up by 2.9 each time. Other times the gap might get smaller. Then in that case, you need to just tweak your answer ever so slightly. Next one, we're asked about things making ester links. Where the esters are formed. False carboxylic acids. You're talking about glycerol. This means that it's an alcohol as OH groups. So it contains, we're making an ester, 3 ester links. It's going to have 3 hydroxyl groups. That is what glycerol has. It is propane 1,2,3 triol. So it contains 3 hydroxyl groups. The OH groups mean that it can make 3 ester links. Next one. Calculation, a proportion question. Look at what we are told. So the first connection we have is that 0.183 grams in, find that in 1 kilogram. I'm going to change that to 1,000 grams. This is going to be there to with. Next, a recommended daily value of 0.0 or 0.15 milligrams of iodine. So that's going to come over here. I want, when I'm scaling between 2 values for the iodine, I want them both in the same units. I am going to decide to make this into grams. 1 gram goes 1,000 milligrams. We are starting at milligrams, and I'm going to turn it into grams. What I need to do is I need to divide it by 1,000, turn it into grams. So instead of 0.15, I'm going to end up with 0.00015 grams. We try to work out how much seaweed would contain that much iodine. When I'm doing my scaling, I always like to go through 1 gram. I want to go from 0.133 to 1. I can divide down by itself. Give us that. Then go from 1 to any number. You just times by the number you want to get to. So, all value of grams there. And I want to do the same on the other side. So the mass of seaweed that will contain that number of grams of iodine be 1,000 divided by 0.13 times 0.0015. 1,000 divided by 0.1 gives us 1 or 3 significant again, so 1.13. That's going to be grams. If you had kept it in kilograms, you'd end up with 0.00113 kilograms. So 1,000 times smaller as a number. Include your units, as long as it matches up correctly, you'll get the mark for that one. Moving on, we're asked about the technique of measuring the mass by difference. First, you need to measure mass of the container you're measuring it in. Measure mass of container. Then mass of container plus your seaweed. Then you want to do mass of, so the difference between them. So mass of container plus seaweed. Take away mass container Another option you could do is if you put your container onto your balance at the 0 or the tare, then add your mass of seaweed. That will get you the mass of the seaweed. This question we're asked about the reducing agent. I would do is split up two equations. We need to figure out where the electrons go in actions. One of the things we can do is use the clip. Got lots of info. Help us down. Please. Iodine I know is going to be on here. What I'm looking for where do the electrons go? What are they beside? They're beside the I2. Back over here, I can put the electrons on right side. What that also allows me to do is decide if that is an oxidation or a reduction reaction. What I can see opposite way around, atoviculates are reduction. And for this, has to be oxidation reaction. Now, without looking any deeper than that, other equation has to have the electrons. Has to be reduction reaction. Redox one of each. With this question, we can approach it again another couple of ways. Said that a few times. The reducing agent, it will reduce other species. What this means then that the reduction has happened to our hydrogen peroxide. Therefore, chemical that caused that to be reduced is a reducing agent. Chemical caused that to happen be our iodide. On to the next one, we're talking about a standard solution. This is a definition you have to get memorized. It is a solution of accurately known concentration. Moving on, got a number of moles of thiosulfate. Asked to work out the number of moles of iodine required to react with that number ratio. Got thiosulfate. Part of the reason I know that, well, I know what the formula is, but also it says that it will react with iodine. Iodine's here. The chemical that reacts with it has to be on. Those are two ways of knowing that's the case. Got Na to S2. It's reacting with. There is a 2 in front of here as a balancing number. That means it's 1 ratio. We have got 0.6. Then our iodine side is half of that. Divide it by 2 gets you 1 3. That is how many moles of iodine got. We're asked to work out mass of iodine in that sample. Well, I know the number of moles. Anyway, first try to use MOFM. So N is the mass is what I find out. Iodine. Diatomic, so that's something we need to take care of, otherwise we're going to get that. 126.9. I'm going to round that and take that to 0.03. That one, if I was going to take it to 329, 9, nah. Correct answer. Next one, first one's just a definition of essential amino acid. These are ones that cannot be made by the body, so must be acquired from the diet. And acquired. Reason it needs to be done, that is body cannot make. This next one, we're asked to draw a structural formula for the dipeptide formed when these two things join together. Forming a peptide link, this is a condensation reaction. And what's going to happen there is we're going to form water. Lose the OH from the carboxyl group. And lose the hydrogen, one of the hydrogens. amine or amino group. When we go to then join them together, to write this, those make my life easier. I'm going to just do them as the H's up and then left. There, we've got carbon. They'll have the carbon double bonded to the oxygen. In this case now, we're going to go to the N here. There. I have my H. What's different about this compared to other questions on proteins is we're only joining two of them. We're not changing the left hand and right hand sides of them. If it was taking a protein, chain was continuing, you would have to do that. I now just need to put all the correct connections in. First one I had a H coming up. CH2, H3. You need to make sure that you connect the S and the C, not the S and the H. You did this is incorrect. On connections, so you mark, watch out for that, make sure the carbon's connecting through. This one, that looks fine. Action's fine with the carbon up here. That, and that gets you answer. That you could do them diagonally as well. I just find something this even technically correct. Next one. Read through the passage and put the correct chemicals in the correct places. Starting off, sulfur is burned in a furnace with excess air. Got that one. This forms a gas mixture that contains sulfur dioxide and oxygen. Got that there. And cooled and passed into the reactor, which contains a catalyst. Sulfur trioxide is formed. After this point, got sulfur trioxide out of it. Passed into absorbers where it's absorbed into concentrated sulfuric acid. That's going into the absorber and it's forming oleum. Something that's being cycled, that's been put back in. Then oleum is diluted with water. That means water. Yeah, so I'm just give uric acid. That will be the bottom answer. Last of all, I saw the word recycling. Unreacted sulfur dioxide is not absorbed, cycled back to the reactor, which is happening here. So this has to take your time following it through. It won't always just be the order it's named in the passage is the way you put it in. This one, sulfur dioxide, was mentioned at the end. One of the ones in the middle. Take your time, work your way through it. This one we're talking about exothermic. Exothermic releases heat. We want to make sure that our reaction works as best as possible. You need to have heat must be moved when temperature rises. Reaction temperature gets too much. It might not work as well, but also there's the danger of it problems happening from that. That's also another cost taking account, cooling it down. Here we're asked to give the explanation of how London dispersion forces arise. We need to talk about an uneven distribution of the electrons first. This causes temporary dipoles to form. These would form attractions with other molecules, which result in the LDFs being formed. LDFs depend on electrons. This would mean that the electron number of electrons in sulfur is greater than that of oxygen. One of the things we should be aware of is that oxygen is diatomic. 2. Sulfur is covalent molecular as well, but it's S8. It's a larger molecule. Other one is 4 for phosphorus. Sticking with these two. Sulfur there's more electrons in the sulfur molecules, therefore they will have the stronger London dispersion forces. Next one, we're talking about using catalyst. Enthalpy change is not affected by a catalyst, it will just stay the same. Enthalpy change is the energy difference between the products and the reactant. But a catalyst will decrease the activation energy. Next one, we're talking about soapless detergents and soap. If you use soaps in areas with hard water, you would end up forming scum. So the detergent does not form scum. Next one, a key feature of this, as a detergent, they have to have an ionic / philic head, valent, phobic tail. So allow the head to dissolve in the water, tail to dissolve in the fat or the oil. You could also talk about solubility, so water soluble head and non-water soluble or oil, fat soluble tail, something like that. Pick up the mark. This one with the name of the ester, you split it in between the ester link. So our ester link is here, split it here. Esters, I did this earlier, from an alcohol and carboxylic acid. Know your functional groups, this will help. It's an OH group alcohol, double bond O, OH. Look at this part here, this would then have to be the acid side because it's got the double bond O. Other side is in alcohol. You should name the alcohol first. We've got 1, 2, 3, 4, 5 carbons. That's going to be pent. Naming process, we put io on the end, so pentyl. 2 carbons on acid side, eth, and it's ethanoate or ethanoate. That's our answer. Split it, identify your sides, name the alcohol part, put an yl, and the acid part with weight, and that will pick up your mark there. For this one, you've got 2 options for the reaction that esters got. First of all, you've got condensation. That also applies to making proteins or peptide links. Other option is esterification. Personally, I would go for the first one because that applies to more reactions. One less thing to remember, but esterification works as well. This question, we're talking about making carbon dioxide gas and asking why we can collect it over water. Got 2 main ways of collecting gas. We can either use a gas syringe like the one at the top, or we can collect over water, which we've got on the bottom. If the chemical dissolved in water, this one would not work. They are saying we can use that. That is because carbon dioxide is insoluble in water. It will just pass straight through the water and we can collect all of it in our measuring cylinder or whatever we use to collect it in, insoluble in water. Other gases, this will not work as well. For next one, little calculation one. Again, told a volume. We are down here told molar volume, so we're going to be dealing with that one again. Last off, we've got GFM for asked about the mass. So I'm going to start with carbon dioxide. One of the reasons, again, why I'm doing that is citric acid we want at the end. Leave everything to do with that to get our final answer. So start off with carbon dioxide. We are told volume. Turn that into litres by dividing by 1,000, 0.05. Also told molar volume. Now I'm going to do this one slightly differently. In one of the previous questions I used equals V M. A slightly different way getting to the same answer. Molar volume tells me that 1 mole takes up 24. We've got 0.055. I'm going to work out how many moles that is. Sticking with the scaling way that I use every time, I divide by 24, get us down to 1 litre is litre. I can times by 0.055 to get up to 0.5 litres. Therefore, for our 1 mole, divide that by 24, times that by 0.5. That will give me an answer. Now, that's actually the same sort of process we do when we use the N equals V over MV equation. Just a different way of doing it. 1 over 24 times 0.05 gives us 0.20229. That is. Next up, if we're dealing with two different chemicals, we need to do a ratio of CO2 to 6. Just check there. If you look up at the top, it tells you what citric acid is. You're not sure which one it is we're dealing with. Therefore, we have got a 3:1 ratio. 3 there, 1 in front of that. If you pick the wrong chemical, you would think it's a 3:3 ratio, which will throw everything off. This means I need to divide my answer by 3. It is small enough as it is. So we've got 0.009. Then we're asked about the mass of citric acid. So M equals N times GFM. M equals that tiny number times 192. Here. So that this time. With this question, we're almost there, not quite, because it does say that we want it for 1 week. Previously in the question, it tells us that's for 5. So if we've got that many grams in 5 weeks, then we want to divide that by 5. Divide that by 5 to get our answer for 1 week. Next question. We're told about specific chemicals. We're given their diagrams and we're asked about different things about them. So first thing, we've got an aldehyde and we've got a ketone. Aldehydes reacting with potassium dichromate. We're going to have a colour change that we need to remember, which goes from orange to green. Next part says what other chemicals could be used. Well, there's 2 of them. There's Fellings. Solution. Other option would be Tollens. Agent. In terms of the colour changes, not needed for this question, but this Fellings goes from blue. So my teacher back in the day told us brick red, reddy orange, orangey red. Something to do with that would work. And the other one forms a silver mirror. Next one, isoprene units. When terpenes were first introduced, I remember myself and the rest of the department I was working in looking up lots of different textbooks trying to figure out what they were on about. The simplest way of describing them is we're thinking in 5 carbon blocks. One isoprene is 5 carbons. We go up to limonene, the one on the left, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. So if there are 10 carbons, that is 2 isoprene units. Answer for that one. Moving on. Another question. Are asked to do some scaling. We are told that change this into grams, so 1 kilogram is 1,000 grams. Then 50. Also told that we've got 5 centimeters cubed. Solution used. So I think we'll figure out how many grams that is. That solution contains 100 centimeters cubed solution. That is 0.0 grams. Now, what I'm looking for connections between the values. When I saw, first of all, this just says it in a line. It's linked together in the words. That's why they go together. I've then got 5 centimeters cubed of the solution mentioned, and it's important to look at what it's referring to. This is a solution, not the natural vanillin. It's when it's been diluted. Then also got another statement that says how many grams are in that solution, and that's the link between the two parts. So I need to turn my 100 centimeters cubed into 5. So I need to scale down the way. You can do this in 2 ways. These numbers are quite nice, so you might have spotted that is dividing by 20. Another thing you could do, if you think about putting 1 in the middle, well, I would divide by 100, then times by 5. You divide by 100 times by 5, that has the same effect as dividing by 20. So either of them work. This one, the numbers are quite nice, so I'm going to stick with dividing by 20. And I need to do that on the other side as well. So I need to divide by 20. Far side, 0.184 over 20. Pop that in. 0.00 grams. Now, I can then use that in my one with the price. Shuffle that around a little bit. But with 1,000 grams, 1,050, then our 0.0092 grams. Okay, so again, let's go through 1 gram this time. I don't know scaling factors for the bottom part, so it's divide by 1,000, and I want to times by 0.0092, and I have 1.50 divided by 1,000 times 0.092, give us how many pounds got. Six pounds. Question asks us it for it in pence, so we need to convert between pounds and pence. 100 pennies in a pound. I want to times that by 100. Gives you 0.966 pence. Round it up to pennies because you can't get that amount of pennies. You would round it to the nearest penny, which would be 1 pence. Which, having gone through all that work to come out with 1 pence, sounds like it's not the correct answer, sounds like it's made up. That is what it would work out to for this question. This question, we're told information about a solution. We are first of all told that 35% solution means it's got 35 grams and 100 centimeters cubed of solution. So to work out the mass of 35%, that would, oh yeah, okay. It'd be 0.525 grams in 100 centimeters cubed. We are told about 300 centimeter cubed. So if we want to work out how many grams would be in 100, we want to times that by 3. Same answer. Times by 3, 1.57 grams. That's a bit. Might be another way we could, another approach, another order you can do stuff in. So we could have dealt with this. Could have dealt with the 300 first, then scale up this value 4.5, and then taking 35% of the 4.5, give us that answer as well. whatever. Quite a lot of numbers floating about there. But that would get us our answer here. We're talking about enzymes. What class of or family of compounds? They are part of the protein family. That's why they can be denatured and change and not work. And let's forget that. Skip. Next one, we're talking about doing a titration. We're asked about accurately measuring out volumes. This rules out any beakers, test tubes, measuring cylinders. In a titration, you want to use a pipette and a burette. So pipette will measure it out your volume into your conical flask, and your burette you'd use tighter. You'd use to slowly add your other chemical until you get to a reaction. Next one, we're asked about the volatile non-water soluble compounds obtained from plants. These are your essential oils. But you could be asked to give the description of them or parts of the description. This one, which you need to recognise, is talking about essential oils. This one, we're asked about the isoprene unit that was mentioned in a previous question. Isoprene unit is a 5-carbon unit. Here we've got 2 isoprene units. Again, this is pretty much a memory one. So there are 4 carbons in the longest chain, which is going to be but. When they are separated, got 2 double bonds. So we have buta, 1 diene. Those double bonds have been broken as they've joined up together. We've also got the methyl group coming off of the second. We have 2 methyl, buta, 1,3-diene. Next question, we're talking about oxidizing them. To be recognizing that we have an alcohol group, or we have the hydroxyl group found in alcohols. This carbon with the OH is attached to 2 other carbons, making this a secondary alcohol. Secondary alcohols are oxidized into ketones. Works is we have primary alcohol oxidized to an aldehyde acid, your carboxylic acid. That got secondary ketone, but then it does not oxidize again. And then your tertiary, there's 3 carbons attached to the carbon with the OH. They do not oxidize at all. No result. Any chemical. Next one. We are making an ester. We have a carboxylic acid, and we're making an ester. This means, going from what I've said a few times in the video alone, this is alcohol. Ester link is here. Means this part on the right hand side has came from the alcohol. I want to work my way back to that. I'm going to break this bond. This would end up with an OH to make it back into the acid. This would have a H make into an alcohol. That means there's 1 carbon. 1 carbon's meth, an alcohol, so it's methanol or methanol. Next one, asked about percentage yield question. Data booklet. Tell us how to do that. So it's percentage yield equals the actual yield over the theoretical yield. The actual yield is what's produced in the lab. The question says that 24.7 grams was actually produced. You're going to need to work out the theoretical yield and then times it by 100. Key is the percentage yield is of a product. The methyl salicylate is. Salicylic acid is our reactant chemical we've got at that. So we're going to use that to try and work out how much should we make of the ester of the methyl salicylate. First thing I'm going to do N equals M for GFM acid. Pop in the numbers, 28.3 over 138. Calculator does 0.205 moles. We want our ratio. Chemicals. Let's easier. That goes to the H8. It is a 1-to-1 ratio. Really, we could ignore the ratio, but I like to just do it in case it's not, just make sure we're in the habit of checking at least. 5 what? Earlier, we have work out the mass, moles times KFM. That's going to be our 0.205 times 102. This is 31.16 grams. Now we can then just go back to our percentage yield part, stick in our 31.16, stick them all in the calculator. Gives you 79 point. Question, another proportion question. We are told that we have toxic level of 0.14 grams per 1 kilogram of mass. We are also told that it's 65 kilograms. This means it's going to be 0.14 times 65. That'll give us 9.1 grams as that's the toxic dose. Question tells us about how much oil white or green contains 7 grams of the methyl salicylate. So we've got to say that we have got 7 grams 5 or 9.1. I'm going to want to divide by 7. Want to times by 9.1. Do that to 5 over 7 times 9.1. Go to our calculator. Go to the calculator. 5 divided by 7. 6.5. Our correct answer. Okay, in this question, first thing I'm noticing is we're talking about water with fats and oils. Emulsifier will help keep them together. So emulsifiers will allow polar water and non-polar fats and oils to stay mixed together. Next time I'm talking about proteins. Proteins are made by condensation reaction of acids. At high temperatures, they can be natured and change their shape. Next up, we've got about the differences between fats and oils. It's their degree of unsaturation. Fats, oils, or carbon to carbon single bonds. And molecules can pack more tightly together, have stronger intermolecular forces. Points. Next up, we've got talking about milk going off. So oils will go rancid. Oils. They have more carbon-to-carbon double bonds, which makes them more susceptible, more likely to act with oxygen. Next, we talked about hydroxyl group. So hydroxyl groups found they can be oxidized, and that again links to oxygen into sides carboxylic acids. Good then. Yes, nah. Try and fit it in here. Could build on that part and say about the fact that if you've got your primary alcohol, so 1 carbon attached to carbon with OH, that will go to an aldehyde. We've got carbonyl group, H, rest of the chemical, go to your carboxylic acid. Bit similar. Secondary. Going where that carbonyl group middle. Probably some more, but that would more than a good answer, and that'd pick up your 3 marks. Next one, we're talking about heating up a chemical reaction using a water bath. This tends to happen when you have flammable reactants or flammable products. So something about flammability would pick up the mark. But let's say what we're using, we're making alcohols, we're using aldehydes and ketones. So reactants, flammable. Next one, the apparatus Y is a condenser. It's used to cool down any hot gases and stop them escaping. In practice, in your class, you might have used a wet paper towel to do the same thing. This is just an ever so slightly fancier version of that. It's called a condenser. Fill everything down. Next one, just a name for the reaction that's shown in step 1. I'm looking to see what has changed. I spotted that we had carbon double bond, and then at the end of this stage, we no longer have that. We now have extra hydrogen also added on. One of the things that makes these questions tricky is they move them around to try and get us a bit confused. What we've got is this carbon here, CH3, this carbon up there. Also then got this, these 2 carbons come from here, or that whole bit come from there. So when you break a double bond, add things to it, that is an addition reaction. Typically a carbon to carbon double bond. This question we're breaking carbon to oxygen. It is an addition reaction. This one we just asked to name this alcohol. You need to include the carbon with the OH, so this one's the most important one. I can see that we can have 4 carbons in a row, not 3, which is what some people would end up putting. 4 is bute. You can look it up in the data booklet if you don't remember them. Have bute. And on the second carbon, the H group, second carbon, so it's butane 2 all. We have 1 carbon branch, which is a methyl group off of the second. So 2 methyl butane 2 all is the correct answer. Next one, we have to draw the structural formula for the alcohol formed when that reagent reacts with pentan 2. Right. That'll look. Then I'm going to base it off of my pentan 2 one. Pent is 5 carbons as it was before. Then got double bond O, the pentan one. Yep. And all H's. So Let's investigate again. I think I know what's happening, but let's double check what happened up here. So the first thing we need to do, that double bond O now going to break, and it's going to allow however many carbons here to join on. First thing, so when we're looking from the start to the end, what is it is different now? We've added on an extra carbon. Okay, so from the start to the end, what we've got is we had 2 carbons in our carbonyl compound, and we had 2 in our Grignard reagent, and we had 4 carbons joined together. So at the end, we had our OH turn into an alcohol, and of the methyl part of the aldehyde, it was then moved up to the top. So it's kind of rotated it around a little bit to try and put the things together. First thing I wanted to know the double bond has to break. And what this does, this opens up 2 new bonds. What happens is a H goes on to one end of the bond, and that makes us have an alcohol formed. So we can see that up here that we've had this carbon, double bond O, now that carbon has the OH. Second thing we need to do is on the other part of it, we're going to add on however many carbons were in our Grignard reagent, which in this case was 2. The one we're asked about, we're told about, again, there's 2 carbons coming on. So all I'm going to do is put my 2 carbons down here. I have C with 2 H's, E, H, D, like that. If we were in the slightly unfortunate question of being asked to name, if you were asked to name this, got 1, 2, 3, 4, 5, 6 carbons in the longest chain. That's going to be X. The OH group this time is on the 3rd carbon, so we'd name from my bottom one here. So 1, 2, and then that gives you 3. So it's hexan, E, all. And then our methyl group this time is off of the 2nd carbon. Other ways you can draw them, you could, if you can rotate them around in your head, if you can figure out where they go together, you could have drawn it with just all the carbons, the 6 carbons I should say, through the middle. Have something like this. Have your OH here. Have your H3 off of there with all the H's in it. That. As long as it's got the correct connectivity, it's got 6 carbons as the longest chain, OH off of the 3rd, as well as EH3 off of the 3rd one. Mark for that one. Last question. We are talking about a technique that's used in advanced higher chemistry. It's dropping this down and making it a problem-solving question. Different types of bonds absorb different wavelengths of light. First question is saying we've got a spectrum obtained from a plastic to make a yogurt pot. We're trying to match this one to our options above. So when I'm looking at the first line on the yogurt pot, we've got one at around about 3000, and it's a triple line that we've got there. We look up above, this one above kind of has that in the same sort of point, but if you look at the other side of it, pattern doesn't really match. So here we've got a long jaggy, a long spike, shorter ones, then another long one. That does not match up what we've got here, so I'm ruling that one out for that reason. On to the next one, polypropylene. Again, not quite the same. We've got one that extends a lot more than our yogurt pot plastic. That one out. Here, this one, quite positive. We've got our matching kind of triple or quadruple spike part here, and we've got our slightly longer sections further along around about 1500. So that's looking quite good. Whereas here you need a big long spike just below I should say 3000. which is not going to be correct. Our answer would be polyphenol ethene. Answer there. This one, we are told a particular value of an absorption and we're asked to find which bond is responsible for that. Yeah, new data booklet is page 15. So we have got to look at the value of 1720. So going down till we get to ones that could be 1720. What I'm seeing, these ones will be there. They have all got something in common. All a C double bonded to an O. Jump back to here, find one of the C double bond, circle that. So the carbonyl stretch would be our correct answer. Final question. We are asked to again use page 15 of the data booklet, and we have to sketch the spectrum that we would expect to see for this chemical. And we only care between 3500 to 2000. What have we got? Well, one of the things I'm noticing, we've got our C triple bond N. Other thing we've got within it is going to be our C to H bond as well. Let's look at the values of them and put them in. I want somewhere around about 2200, just above 100 here. Going up, I would say in 100, so 20 or 2000, 2100, 2200, and I want just beyond that. We need this spike round about there. Then for the C to H bonds, that here, that's going to be just around about 1400, call it. Although that's going to be too small, because we're limited to being at 2000. Different one we could have. Not got them, not got them. This one's looking promising. Around about 2800. 2800. About something like that. Now, I make it look somewhat like these ones. So we come along and down. This. Start here, we'll go across so we get to in that range we're talking about. Down. Come back up. And go along until we reach the next part that we want it. Down. Other. There. And end. Those lines. Main thing is that the position of the peaks is in the right place. So as long as you have them in around about the 2700 to 1000 range, pick U. And then as long as you have it within the 2200 type one, which again we do have it popped in there. And that is the end of the paper. That's how I would have approached the 2021 Higher Chemistry paper. Thanks for watching. Bye bye.